2:15. All right. Where were we? Here we go. So let's take a look at the first problem. You can see there's definitely a change to the carbon skeleton. In this one, we're starting it with what? 1, 2, 3, 4, 5 carbons. And then we're ending up with 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we're adding a total of 3 carbons in the process here. So we're adding 3 carbons. So we have 5 carbons here. We have 8 carbons here. And then also we're ending up with a cis alkene in the end. But I know that we only know one way to do this. So I don't want to annoy you guys by asking the same questions over and over. But could anybody tell me what the first 2 steps are going to be for this one? Can anybody just kind of guide me through it? Yep. So it's not going to be ethyl iodide because I need to add 3 carbons, right? Right, so I need to add a total of 1, 2, 3 carbons. So instead of ethyl iodide, I would use propyl iodide. All right. Okay. Yeah. So step 1. So we'll say here we have our starting alkyne. So step 1 is going to be to treat it with sodium amide. That's going to give us the alkanide. Step 2 is going to be to treat it with propyl iodide. That's going to give us 1, 2, 3 carbons. And then to make the cis alkene, we're going to treat it with H2 and Lindlar's catalyst. That's right, Lindlar's catalyst. Or if you just want to put poison to catalyst, that's totally fine too. So that's a total of 1, 2, 3 steps for that one. The next one is kind of an interesting one because we need to add 3 carbons, right? We have a total of 6 carbons in this compound, and we have 9 carbons over here. And you can kind of tell that you need to add these 3 carbons over here. And the kind of the interesting part of this one is that if you remember, I told you that if you need a little reagent with just a few carbons, you can have that. So in this case, you're going to need the propyl alkanide like that, which is a good nucleophile. So what that means is if we take our starting material, so if we take the starting alkene and we treat that with HBr and peroxides, that's going to give us this compound, and then we can treat it with our nucleophile, okay? So that's going to do our SN2 reaction. So our SN2, which is going to give us this compound. So just do 1, 2, there we go. 1, 2, 3. Not my best artwork. Let me fix that a little bit. I don't want this on the internet. There we go. That's a little bit better. And then to reduce it to the transalkene, we're going to use sodium metal reduction in liquid ammonia. So again, that's another 1, 2, 3 step synthesis. And what about the last one? The last one is kind of longer. So let me just, let's see. I don't even have a blank document here, do I? I know where we can find some space. We'll do it right here, okay? On the schedule. There we go. All right, so if we start out with this alkene, and then we want to make this terminal alkyne. This one is going to be kind of another kind of foray into retrosynthesis. So if you remember, this arrow is a retrosynthesis arrow, right? And if I was to have this compound, okay, and I treated it with sodium acetylide, right, then that's going to give me the final compound. So now the question becomes, well, how do I get from here to here, right? How do I get that bromine on the end? So could anybody tell me, should my first reaction, should it be a Markovnikov addition of HBr or an anti-Markovnikov addition of HBr? Exactly. Thanks, Mustafa. It's going to be anti. So I'm going to treat it with HBr and peroxides. And that's going to give me this compound. Now I want to make the Hoffman alkene. And so to make the Hoffman alkene, I'm going to use a hindered base. And then to make that primary alkyl halide, I'm going to use another anti-Markovnikov addition of HBr, like that. So that is going to give me the primary alkyl halide, and then in the last step, I'm just going to treat it with sodium acetylide, and I'm done. So this one is a what? 1, 2, 3, 4-step process. So a lot more of an involved process, this one. But again, you remember this arrow is a retrosynthesis arrow. So it's got 2 lines and then a head on the arrow like that. So that's a retrosynthesis arrow. And we use that to think backwards. If we get stuck on a problem, we say, well, you know, the last step must be this, and then we can kind of work backwards from that. So if we go back here, okay, so what do we say about that? It is right here. So retrosynthetic analysis is just the art of doing the last step first. Okay, so we solve the last step first, and then, you know, we keep going backwards. So as always, you're going to ask yourself, is there some kind of change to the carbon skeleton? Is it getting bigger? Is it getting smaller? And then analyze the functional groups and just say, okay, well, what do I have to do, you know, to move those around? So for this one, for example, there's a number of ways you could do this, but to make an alkyne like this one, if there's no change in the carbon skeleton, right? We're starting with 4, 5, 6 carbons, and we're ending up with 6 carbons. So that tells us that the retrosynthesis, we must have to have this compound, right? We have to have that compound because then we could treat it with excess sodium amide. But then the question becomes, well, how do I make that compound? Well, this compound has to come from this alkene, right? And then it's like, well, how do I make that alkene? Well, I could convert the hydroxyl into a good leaving group using tosyl chloride and pyridine, and then I could use the appropriate base to make that alkene. So you can see all the steps are shown here, but again, retrosynthesis is focusing on the last step first. So I think you guys could figure that problem out without any of my help whatsoever. So when we get to the end, here's the whole thing. You treat it with tosyl chloride, a hindered base to mitigate the SN2, so you get the E2, then bromination, excess sodium amide, and water to give you the product. So it's a 5-step sequence, but again, this is the kind of reaction sequence that I would expect you to be able to figure out. So with that in mind, let's try a couple more problems. So we'll start with an 11.9b. Okay, so we're starting it with 1, 2, 3, 4, 5, 6, 7 carbons, and 1, 2, 3, 4, 5, 6, 7. So we have 7 carbons and we have 7 carbons. Now, in terms of retrosynthesis, what functional group must I have to have in order to make this methyl ketone? There's only one possibility based off of what we learned. Yeah, an enol, but the enol comes from what? You're right, the enol tautomerizes to give you the methyl ketone, but the enol comes from what before? Because enols are unstable, generally speaking. Anybody? What would this have to come from? What would the enol come from? Exactly, an alkyne. Yes, sorry, I ended up with a problem. There we go, an alkyne. Right, so it has to come from an alkyne. So if we have 1, 2, 3, 4, 5, right? It has to come from this compound. So now the question becomes, well, how do I get from here to here? Well, you use excess sodium amide followed by water, right? So let's scribble some of this down. So I'm just going to write it down. I don't know. Don't have a lot of space here, but we'll scribble it down right here. Okay, so we're going to take our starting geminal dihalide, and we're going to first treat that with excess sodium amide, and then water, and that's going to give us so hard to draw on the iPad at an angle. At least it is for me. There we go. Like that. And then the last step is going to be to treat it with, to do a Markov-Nikov addition of water across the triple bond. So we're going to need mercuric sulfate, sulfuric acid, and water. And like Anna said, you're going to end up with the enol. So you're going to end up with this compound, but this compound is unstable, and it's going to tautomerize to give you this compound. So remember, this is tautomerization. All right, because the enol is unstable. All right, let's try the next one, C. So I'm going to have to scribble it down over here. I've written a copy of it here somewhere. There we go. Okay, so in C, no, I have the wrong one. Where am I? Oh, I have the wrong one. So I'll just scribble it down here. So we'll say we're starting with 1-butene, and then we want to make cis-3-hexene. So let me just take this guy. We'll paste it down in here. There we go. All right. So in order to add carbons, I'm starting with 4 carbons, and I want to end up with 6 carbons. So that means if I'm adding 2 carbons on the end, retrosynthetically, I'm going to have this compound at some point, and then I'm going to treat that with ethyl iodide, and then I'm going to have to reduce it to a cis alkene. So now the question becomes, how do we get from the alkene to the alkyne? Well, we've covered this already today a couple of times. The first step is going to be to treat it with bromine, okay? And that's going to give you the geminal dihalide, like this. The next step is going to be to treat it with excess sodium amide, followed by treatment with water. Oops. Followed by treatment with water, which is going to give us this compound. And then the last, well, actually, there's a couple steps at the end, so maybe I'll prolong it here. So step 1 is going to be sodium amide, and then we need 2 carbons, so we'll add ethyl iodide, and so we're going to end up with 3-hexyne. But if we want to make the cis compound, we're going to treat that with hydrogen gas and Lindlar's catalyst, and that's going to give us the cis alkene. All right. Give me a thumbs up if you follow me on that one. Any questions about that one? Okay, let's try one more. Let's see here. Oh, D is kind of an interesting one. We'll do this one in blue. There we go. So we end up with this compound, and we're trying to make acetone. So we're trying to make some nail polish remover. Let's see here. Oops. There we go. So we'll just paste it down here. All right, so if I want to do this transformation, what's that going to look like? Anybody solve this one? Could anybody give me a strategy of where you might start with this one? Because you're going from 6 carbons to 3 carbons, which is kind of funny. You're cutting it in half. Anybody have an idea where to start with this one? I'm genuinely interested in what my students have proposed. No? All right, would I start out with a Markov-Nikov addition of HBr or anti-Markov-Nikov addition? Does anybody have an idea about that? No? Okay. I'd probably start it with a Markov-Nikov addition, right? Because that would give you this compound. If I started with an anti-Markov-Nikov addition, I'd end up with this compound. And then I'm not sure how that would get me closer to the ketone. That one, let me just move it out of the way here. So, but if we do a Markov-Nikov, right, then we can treat this with an unhindered base, like sodium methoxide, and that would give us this compound, and then we can just treat it with ozone and DMS. And we're going to actually double the quantity of product. We're going to get 2 moles of this for every 1 mole of the starting material. All right, so really clever synthesis, that one. And so green chemistry is just dealing with, how do we prevent waste? Being organic chemists, we're trying to find ways to maximize the use of our atoms and our reagents and minimize waste. So green chemistry has 7 guiding principles. The first one is to prevent waste. Use less hazardous substances. So trying to avoid things like osmium and mercury, iridium, dangerous elements, using safer solvents. So benign solvents, so ones that don't have chlorine in them. So avoid chlorinated solvents. Maximize atom economy. So that just means if there's any atoms incorporated into the reagents, that they end up in the product and not in the waste container. So take a look at these 2 reactions here. This is nothing more than just a Markov-Nikov addition of water across this double bond. Okay, it's all it is, just a Markov-Nikov addition. Well, you guys know you can do it with H3O plus, right? So that's a catalytic amount of H plus proton plus water, right? You mix those together, you get hydronium. Or you can do it using oxymercuration, demercuration. Well, why do I not give students full credit when they use this when we don't need it? It's because there's all the atoms that are in red, they all go in the garbage can. Okay, they all go in the waste. Whereas with this set of conditions down here, the only thing that goes into the garbage can is the H plus ion, and that's catalytic anyway. So it basically creates virtually no waste whatsoever. So everything is incorporated into the product. And so this reaction has a good atom economy, and the one on the top has a very poor atom economy. This was developed by a chemist by the name of Barry Trost. And I think he's at the Scripps Institute in La Jolla, California. Anyhow, what else? Use catalysts rather than stoichiometric reagents. So using things like a catalytic amount of osmium tetroxide versus a stoichiometric amount, 1 mole to 1 mole ratio. Energy efficiency, of course, if you can do a reaction at low temperature versus high temperature, it saves electricity. And then renewable feedstocks, using things like corn as a way to get your carbon, containing starting materials instead of getting them from petroleum products. So how do you master your syntheses from organic 1? I mean, really, we talked about reactions that alter the carbon skeleton, so ozonolysis, and then using an alkanide or an acetylide, and then reactions that alter functional groups, converting a hydroxyl into an alkene, so on and so forth. But again, the main thing is going right back to the first 2 questions, okay? Not to, beat this with, a stick or whatever, but you've got to master all of the reactions in this question, and then all of the reactions in this question. And this is really just the beginning, because you also want to master your SN1, SN2, E1, and E2 reactions. But really, if you have a solid understanding of those, it gives you a good foothold to start organic chemistry 2. And so, let's see. Okay, where was I? All right, now, as we move forward in Chemistry 3111, so now we're in the big leagues, we're in Organic Chemistry 2, and what you'll find is that as we move forward in this class, not so much right now, but as we move forward in Chemistry 3111, this class, you're going to find that sometimes there's going to be more than one way to do a synthesis problem, and both of them are correct. And so, let's say somebody solves a problem in 3 steps, and then another person solves it in 9 steps. Well, 3 steps is going to be a better answer, and so it's going to be worth more points. And so we're always trying to find the most facile synthesis, the easiest one we can. All right. So you can see that if we want to convert this alkene to this alcohol, you can just do an anti-Markov-Nikov addition of water, or you could do an anti-Markov-Nikov addition of HBr, and then just do an SN2. Either one is worse, or either one works. There's no problem with either of them. They're both great. They're wonderful. They both work. You can't argue with either of them. But again, we try to find the shortest route possible. So with that in mind, let's see if we can propose an efficient synthesis to a couple of these guys, okay? I'm going to skip these ones for now. because I feel like we've covered a lot of these reactions many times. But I want to try these ones because some of them are a little more challenging. So let's start with 11.21b. So we're starting with that molecule that was kind of the first, I think the first molecule we looked at in this whole chapter was isobutylene. And then we want to convert it to this aldehyde. Well, based off of retrosynthetic analysis, we know that here we have 4 carbons, and here we have a total of 1, 2, 3, 4, 5, 6 carbons. We know that the aldehyde, we only know one way to make an aldehyde at this point. And so this aldehyde, 1, 2, 3, 4, 5, 6, must come from this alkyne. So then the question is, well, how do we get from here to here? How do we get from isobutylene to that alkyne? So the first step is going to be to take my isobutylene. Could anybody help me with this? Would I start with a Markovnikov addition of HBr or an anti-Markovnikov addition of HBr in this case? Again, I'm talking about this reaction, B. Yeah, anti-Markovnikov, isn't it, Kristen? Right, if I do HBr and peroxides, it's going to give me the primary alkyl halide. And then I can treat that with sodium acetylide, right? And that's going to do my SN2 reaction to give me the terminal alkyne. Now, to make the aldehyde, we know that we have to do an anti-Markovnikov addition of water across this triple bond. I'll just ask you guys, can anybody tell me the first step? Step 1. If I want to make the aldehyde, what's the first step in the anti-Markovnikov addition of water across that triple bond? Must be 9 BBN, right? So 9 BBN followed by H2O2 and sodium hydroxide, and that is going to give me the final product. 1, 2, 3, 4, 5, 6. And there you go. There you go. You end up with the aldehyde like that. All right, let's try C. So in C, we're starting with the exact same starting material, but we want to make this carboxylic acid. Well, here we're starting it with 4 carbons and we're ending up with 5 carbons. Now we don't know any way to add 1 carbon to a molecule, but we know how to add 2 carbons to a molecule. We just did that in the previous problem. And if we could take this compound and just treat it with ozone, followed by H2O, that would give us the compound that we want. We'd end up with the carboxylic acid. Could anybody tell me what the second product would be in this case? So this carbon is going to be this one here. But what would happen to the yellow carbon? You can see it. Maybe I'll make it a green carbon. What would happen to that green carbon? Exactly. Thanks, Mustafa. It ends up in CO2. So there you go. We've solved that one already. So it's going to be HBr and peroxides, which gives us our primary alkyl halide. Then we're going to treat it with sodium acetylide. That's going to give us the alkyne. Again, hard to draw these things at an angle. So we end up with this, and that. And then to give us the final product, step 1 is going to be ozone, and step 2 is going to be H2O. And then for the final one, we're starting it with 5 carbons. So 5 carbons, and then we end up with 1, 2, 3, 4 carbons. Oh boy. So this is another one that we're going to have to cut it up somehow. So let's see here. If we want to end up with that aldehyde, we could make that from another ozonolysis reaction. If we had this alkene, right? We could do an ozonolysis on that and we could end up with the aldehyde. So now it becomes the matter of how do we get from this alkene to this alkene? So could anybody help me out with that? Would I start with a Markovnikov addition of HBr or anti-Markovnikov? So the first step, would it be Markovnikov addition or anti-Markovnikov addition of HBr? So not for this one, right? Because I would want to move the bromine over here onto this position. So it's going to be anti-Markovnikov. So I'm going to use HBr and peroxides, and that's going to put my bromine right here. And then I can use a hindered base like potassium T-butoxide to give me the alkene. All right. And then once I've got the alkene, I can just do an ozonolysis on that. So step 1 is going to be ozone. Step 2 is going to be DMS. And I'm going to end up with the aldehyde like that.